Hello everyone. So this video is in continuation with the analysis of multi-story frames in part 1, where we have calculated the loads coming to the frame. So in the last video we have seen there was two-storied building and each of 5 meter length and height was 3 meter. So we have calculated the UDL on the beam and the lateral load coming to the every floor. So this was earthquake load we have calculated, and the dead load and plus live load coming to this beam. So in this video we are going to analyze the structure. So this is the part 2, where we'll be using the method of substitute frames to analyze this frame building, but this method is only for vertical load. So we will be only analyzing for vertical load. So only this. In the part 3 we will be analyzing the structure for the lateral load using portal method. So already portal method also video I have given, but for this frame I'll be giving another video so that we can continue, and then we will do the design. Once we will do the structural analysis, we can design the members. So the dead load that we had calculated for the beam, 6 kilonewton per meter, and the live load was 8.44 kilonewton per meter. So how these values have come, you can refer the part 1. So total load on the beam is 6 plus 8.44 is 14.44 kilonewton per meter. Okay. So here also 14.44. So coming to this method name, method of substitute frames. So in this method, a small portion of multi-story frame comprising of floor beams with columns above and below floors assumed to be fixed at far ends is analyzed using moment distribution method. So one video in playlist structural analysis, I have solved moment distribution method of a continuous beam of 3 spans. Here we'll be analyzing for 2 spans, and as the loads are also same and the spans are same, it will be more easy to solve. So moment distribution method. Okay, for vertical loads. So in this method, a small portion of multi-story building. So let me name this joint as A, here B, C, D, E, F, G, H and I. So what we are going to do is, we are going to take a small portion. Okay, so we'll take this portion, because multi-story may be of some 7-storied, 8-storied, okay, any story building. So only one small portion of multi-story you have to take, and we have to analyze that using moment distribution method. So if I am considering this small portion, so I am considering D, E and F, okay, under UDL. So this method is mentioned in clause 21.4.1 of IS 456, that we can approximately analyze this multi-story building. So when you are analyzing the structure using this, there are many combinations. That means dead load plus, if dead load is there in one span, and dead load plus live load in one span, the other span should be empty. Otherwise, if it is 3 spans, you can put alternately live load, because it's not necessary that your live load is always present, right? It can be alternately. So sometimes the effect may be different. Okay, the critical combination can be different. That's why many combinations you can do for analyzing. So here I'm taking the whole dead load plus live load together and analyzing this structure. So it says we have to take a small portion comprising of floor beams with column above. So there is a column above G here and below. Okay, there, and you have to consider this as fixed ends. Okay, the ends we are assuming it as fixed. So we are going to analyze this using moment distribution method. Okay. So these are A, B, C, and this far end is G, H, I. Now, so in moment distribution method, we have to calculate the fixed end moment and distribution factor in the first step. So if I'm taking the fixed end moment, so fixed end moment, so it is WL square by 12 because it's the UDL W. So here UDL is 14.44 into the span length is 5 meter, 5 square by 12. So we have got 30 kilonewton meter. Okay. Now distribution factor will calculate. So at D we have 3 members. One is DE, the beam, and the column above DG and column below DA. So this distribution factor will be same as what will be at point F. So I'll calculate one of this at DE. So your the stiffness will be 4EI by L. So how this formula 4EI by L has come, that is also there in this same playlist video I have made, how this carryover moment is half and how the stiffness matrix is 4EI by L and how distribution factor is calculated. So 4EI by L, so DE, the length is 5 meter by summation of all the stiffness. So 4E by, for DE is 4EI by 5 plus for DG is 4EI by L, means length is here 3 meter, so 4EI by L. Same below also length is 3 meter. Okay, so this comes 0.3125. It's 0.23. Okay, for DE, yes. For DG and DA it will be same because we have same length. So the formula is 4EI by L is 3 meter, the column height is 3 meter because this is 5 meter and these are 3 meter, by summation of all the relative stiffness, all the stiffness. 4EI by 5 the same, 4EI 3, 4EI by 3. So this comes to be 0.385. So here next we have at point D, point E. So for E, we have four elements joining at point E. So we have E, D and EF. Here stiffness will be same because they are of same length. Then we have E, B, the columns. Okay. So for EI by length of ED is 5 meter by 4 EI by length of ED, length of EF, then length of EB. So 4 EI by 3, 4 EI by 3. In the same manner, here we will have 4 EI by 3 meter for the columns, then summation of all the stiffness of the 4 members joining the point E. Okay, so this comes to be 0.3125 and this is 0.385. Let me calculate again. So this is at ED 4 E by L by summation of all the relative all the stiffness is, so this comes 0.1875 and EB is coming 0.3125. Okay. So we have calculated the distribution factor. Now we are going to analyze this frame using moment distribution method. So I'll make the columns. So let me write down, otherwise we'll make a box. First element is D. So this is connected to E node and then is F. So these are the beams. With this we have G column and we have A column. Similarly at this we have H and I, we have B and C. Now I'll write the distribution factor for the DE. Okay, this is for DE. We have 0.23. For DG, okay, for this column DG we have 0.385 and for, I'll write here for DA column, the below one. So for DA column we have again 0.385. Okay, these are the distribution factor I'm writing. Then for F also it's same, so I'll put here 0.23 for the beam. For FC column we have 0.385 and for FI column 0.385. Okay. At point E we have 4 members, so this is for ED, the distribution factor is 0.1875. Then for EF we have 0.1875. Then for EH we have 0.3125. So for EB, I'll write here, for EB we have 0.3125. So writing the fixed end moment. So we have calculated the fixed end moment as 30 kilonewton meter. So if D is the span, the the fixed end moment will be minus 30 here, plus 30 here. Okay. Similarly for EF, minus 30, plus 30. Okay. This is the fixed end moment. Now, coming to this, so you see at E point, we have plus 30 and minus 30. So there is no unbalanced moment. Okay. But coming at D, we have minus 30. So we have unbalanced moment. So this minus 30 will be distributed all over. So minus 30 will be distributed at all these three members like DA, DE and DG to make it balance. So what we do? Minus 30 into 0.23. This distribution factor. If you multiply 30 into 0.23, 6.9. So as the sign is minus 30, we will put a plus 6.9. So so for the column DA, 30 into 0.385, this distribution factor. So we are getting 11.55. As distribution factor is same here, for this column also 11.55. So these are plus. So now if you add all minus 30 plus 11.55 plus 11.55 plus 6.9, it will come 0. So there is no unbalanced moment. Okay. Similarly at point F also, as it is plus 30, we will add. So minus 6.9 it will be minus 11.55 for the column. So this is for F. C, and this is for the beam. This side I am writing for the beam FE, and the above is for FI column. Okay. So above also minus 11.55. Now this 6.9 moment will be carry over, half will be carry over to this end. So half of 6.9 is 3.45. Similarly from minus 6.9 carryover will be half. So minus 3.45. Okay. So you see at point E again plus 3.45 minus 3.45. So there is no unbalanced moment. If you add, it becomes 0 again. Otherwise, if you see the unbalanced moment, if it would have there, for example, if here it is plus 3 and here it is minus 2. So 3 minus 2 is 1. So 1 would have been multiplied with the factor 0.1875 to come at this point here, into 0.3125 to come here moment, and 0.3125 here, then again 0.1875 to come here. So you would have distributed the unbalanced moment all over. But here, since the moments, there is no unbalanced moment, so we are not going to have any further calculation at this point. Okay. So if you refer the moment distribution of continuous beam, which I have solved for 3 span, you can see the difference. Okay. So next 3.45 we have come here. So as the moment is 3.45 from here, again half will come to this end. So that is plus 1.725, and here it will be minus 1.725, half of this. So this 1.725 is unbalanced at point D, which we will again multiply with 0.23, we'll get, and we'll put minus because we are going to balance it. So it's 1.75 into 0.385, the distribution factor, we'll get for the column minus 0.66, and here minus 0.66. Similarly, minus 1.725 at point F, we are going to multiply with distribution factor. We are going to get here plus 0.4. Here we'll get plus 0.66. 0.66. Okay. Now again half will go here. So we are going to do till a small value is going to come. So minus 0.2. here, and here it will come plus 0.2 from here, half carry over. Okay, so minus 0.2 half again coming to this, because again at point E there is no unbalanced moment, so it's 0, so 0.1. Now this 0.1 will be distributed all over, so 0.1 into 0.23, so 0.023, here plus 0.0385 if you multiply with 0.385. Okay, so as this value 0.0385 is very small, here it will be minus. We are going to stop here. Okay, so we are going to stop here because this 0.023 is very small. Now coming to this, we are going to add all the moments. So for this column DA, the moment is 11.55 minus 0.66 plus 0.0385 is plus 10.93. This is the moment coming to the DA column. That means add D to the column DA. Okay, this is 10.93. For DG, same 10.93. Then for the beam DE, we are getting minus 30 plus 6.9 plus 1.725 minus 0.4 minus 0.1 minus 0.23. Okay, this all we are going to add for this. So we are getting minus 21.85 kilonewton meter. Okay. Similarly, here we will get minus 10.93, here plus 21.85, here minus 10.93 for this column. And if you see EB here in this column, the moment is 0. Okay, here the moments for this interior column is 0 due to the vertical load, because it cancels out. Then coming to the moment at the ED beam, so plus 30 plus 3.45 minus 0.2. So we are getting 33.25. Here minus 33.25. So this is your moment distribution method. Okay. So using moment distribution method, a small portion of multi-story frame is analyzed, which is known as substitute frame method. So coming to the bending moment diagram, what we have got. So we had 3 points, D, E and F. So here so at DE we got 21.85. Okay. Here also 21.85. At middle 33.25. Okay. So this is the negative moment. Now we are going to superpose the positive moment. So if you draw the simply supported case individually, okay, for both the span, what is the value? WL square by 8 is your bending moment for the, so for the simply supported case, your bending moment is WL square by 8. W is here 14.44 into span is 5 square by 8, so you get 44.125 kilonewton meter. So these are the positive moments. So you are going to superimpose the negative and positive moment to get the bending moment diagram as so this is, if you add 21.85, here it is 0, so you will get 21.85. Similarly here it is 0, 30.25, and at this end also you are getting 21.85. So this will be your bending moment diagram. So at the center, if I take the positive moment, so you have 44.125, and what will be the value here if I put like this? So this value is 33.25 minus 21.85, 11.4. So if I do 33.25 minus 21.85, this is 11.4. So at the center means half of this will come. If similarity of triangles you put, half of 11.4 is 5.7. So 5.7 plus this value is 21.85, because this is 21.85. So at the center you have 27.55. Here also at the center you have 27.55. So 33. 5.7 plus 21.85. So at this center you have 44.125 plus, this is minus 27.55. So your value is 16.575. So these are positive moment and those are negative moments. This is your bending moment diagram for this DEF. So if you, it's not 16, it's 17. So 40, this is not 44, this is 45. So we calculated here 44.125. So this is 45.125. So 27.55. This is minus plus 45.125. You get 17.575. This is your bending moment diagram. Okay, this is also 17.575. Okay. Now we are going to draw the shear force diagram from this, because when you are going to design the beam, so we are going to take this moments for the vertical load. That means at the left we will take a design for 21.85, at the center for the 17.575. Then if you are taking for this is, if you are designing for this D and E beam, so central moment 17.575, and at E or the left end 33.25. So you are going to design for this three moments for DE. For EF, so you have to consider right end 33.25, center 17.57 and 21.85. So all the moments are in kilonewton meter. Okay, these moments we have to consider for designing, which we will do in next part. So coming to the shear force diagram, we have, there is two methods you can calculate the shear force. First method is if you are considering as simply supported beam, so you will have WL by 2, okay, like we did for case WL square by 8 for the moment, positive moment. So WL by 2, so your W is 14.44 into span is 5 meter by 2 you get 36.1 kilonewton. So this is 36.1, 36.1. Okay. Then for the negative moment, we are going to add. So negative moment, we know shear force is difference of the moment by the length distance. So we have got 33.25 and 21.85. So difference of this two moment is 33.25 minus 21.85 by the change, the distance 5 meter. So this is 2.28. So we can take as 2.28 downward and upward 2.28. So as you added this, your RA will be, RD will be 36.1 because this is downward. So minus 2.28, you will get 33.82 kilonewton. For RE, so similarly you will have the other span, so RE and RF. So here also you will get 33.82, and here you will get 36.1 plus 2.28 because the direction are same upward. So you will get 38.38. Same for here also you will get. So if you add at RE, you will have 38.38, 76.76 kilonewton. Okay. So if I draw D, E and F, your shear force diagram will be here RA 33.82 and here 38.38 for this. Again here 38.38 and here downward 33.82. So this is your shear force diagram. So you see at reaction at point E, we have 38.38 plus 38.38. This total will be your RE 76.76 kilonewton. Force diagram. Okay. Another method here I will do to calculate the shear force diagram, which I have done in moment distribution of continuous beam video also. You may find it more easy also. So if you know what we know, that moment at E is minus 33.25. This moment is minus 33.25. So moment at E, we can write RA into 5 meter at point E. So RA not RA, it's RD. So at this RD into 5 meter minus the moment here is already 21.85. So minus 21.85 minus the load that we are having. So now this is your, so this is RD, RE, RF. So RD, I am taking moment at E because we know moment at E is minus 33.25. So RD into this distance 5 meter, and we already know that moment at D is, at D is 21.85 minus the UDL 14.44 into the 5, the span into the CG distance 5 by 2. So 5 square by 12, right? 5 square by 2 is equal to minus 33.25. So if you calculate, you will find RD is equal to 33.82. It's same as what we calculated in by using method 1. Okay, anything you can use. Now you know RD, so we know RD plus RE plus RF is equal to total load. That means 14.44 into total distance is 10 meter into 10. Total load, total upward force is equal to total downward force. So RD, this is also equal to RF. If you take the moment from this direction, RF into 5 minus again 21.85, this is equal to minus 33.25. You will get RF also same reaction, and also the load and span are same, also directly we can write down. So RD we know 33.82 plus RE we have going to find out, and RF also 33.82. This is equal to 14.44 into 10. So only unknown is RE. So if you solve this, you are going to get 76.76 kilonewton. Okay, shear force. So once you know our reactions, so this is your shear force diagram. Okay, so we have calculated the beam shear force and beam moment, because using this moment and shear force you are going to design. So coming to the column, so we have column G, D, and this is A, and there is another column H, E, and this B. The last one is similar to this side. So here if I'm considering, because we have taken this frame, we have solved this frame, so at DA, okay, so we have already calculated what was the moment that we have calculated. So for DA column, moment is, see, look at the moment distribution method, we have calculated for DA is 10.93. okay, same for the DG also, 10.93 moment is coming. So for 10.93 kilonewton meter, and your axial force will be the, if this is the beam, so now we found that there is a, here reaction is there, so this shear force will come as axial force to the column. So your P will be your RD, so which is 33.82 kilonewton. Okay, so this column. Now if you come to the, so this we have designed for vertical load. So when you are taking the axial load, you have to also add the self weight of column. Okay, we'll add the self weight of the column plus axial force that comes from the column above also, because if this is the column, your axial force will transfer till to the foundation. Okay, so there is only one column above, so I'm going to add again the same 33.82 for the column above. So this will be the, so if you remember the self weight of the column that we have calculated, was 15 kilonewton, 25 unit weight into 0.4 into 0.3, because we have taken 400 cross 500 dimension into 3 meter length, so plus 15. So your axial force will be 33.82 twice plus 15, 82.64. So this is your axial force, and this is your moment for the column DA. For EB, if you see, your moment was 0, so there is no moment, only axial force will act, and axial force is 76.76. So this again above 76.76 will come, plus the self weight 15. Okay, so these are the forces in the beam and column we have found out using method of substitute frame. So after this we are going to analyze the same frame for the lateral load. Then we'll go for the design, because we have to add the vertical load as well as the lateral load forces for the design. So hope this video is helpful for you. Thank you for watching.